Hello ladies and gentlemen, and welcome to the next in this year's series of educational webinars on material characterization, entitled Basics of Extensional Rheology. Before we commence with the webinar, which will last for approximately 1 hour, I would like to draw your attention to the Q&A text entry box at the bottom of the screen. We encourage you to type questions you may have at any time during the presentation, so that these can be answered at the end during our general Q&A session. This webinar is being recorded, and you will be sent a link to the recorded presentation once it has been prepared for publication. The presentation itself will also be made available to you for viewing in the near future. So without further delay, I'd now like to hand you over to the presenter, Dr. Jan-Philipp Plug, Group Leader Rheology Applications, who will be your moderator for this webinar.
Thank you very much for the introduction, Peter, and welcome also from my side. As Peter mentioned, my name is Jan Plog. I work here in our Karlsruhe headquarters for the MC material characterization business of Thermo Fisher Scientific within applications for rheology. And the topic of today's webinar is the extensional characterization of fluids, basics of fluid characterizing with extensional devices, mainly the CaBER I'm going to talk about, CaBER for capillary breakup extensional reometre. Before I'm going to jump into the presentation, let me run you through the agenda here very briefly. I want to start with a basic introduction to extensional rheology. Why do we need it? What is it? How does it look like? How does it differ from normal shear and oscillatory rheology? Before I want to jump into different practical examples in terms of industrial processes and applications that will show you how extensional flow behavior can actually solve questions that shear and oscillatory behavior of specific samples will not be able to answer. Okay, I want to close then with a short summary. So why is there a need for extensional rheology at all? I mean, some of you might know already, when you work with extensional rheology already, that samples that can behave very, very similar in rotation as well as in oscillatory shear flow, those can show still pronounced differences in your everyday's processes, in your everyday applications that your products, that your formulations will face. And I will show you that those differences derive mainly from the extensional behavior. Most of you might know that those extensional properties that we need to investigate cannot be quantified with a rotational device, a Thermo Scientific rotational reometer or a competitive instrument, but that we need other means to do so, and I'm going to present how that looks like. As I said already, many relevant industrial processes and flow fields incorporate extensional deformations, and I'm going to talk about that in detail a little bit later on. So we still see a very steeply increasing interest in extensional rheology and extensional properties in R&D as well as in QC. This is why we do this webinar, of course. So some of you that might know about extensional rheology and might have used different approaches in the past. Here on this slide, you just see a scale of different viscosities and the methods that are still or were available in the past to test extensional properties of fluids. When you go from the low end scale here, from 10 to the minus 2, 10 to the minus 1 Pascal seconds, you see here very old traditional approaches. Some of you might have heard about them, some not. I don't want to spend too much time here, but you might have heard about the opposed jet approach, something that the company Reometrix commercialized back in the 80s with the so-called RFX, or the four-roll mill, or flow-through porous media. That traditionally there have been approaches for extensional measurements on fluids. However, those have usually the drawbacks that they are very time and sample consuming. Okay, and those two effects are of course not very much liked. On the high-end side of the viscosities, there have been different approaches. Meissner machine is one. Some of you might have heard about the Münstedt device that was also commercialized back in the late 80s by Reometrics. However, those machines that are well described only work for very, very high viscosities, very high viscous polymer melts up to semi-solids. There was nothing really commercially available for the fluid area until the CaBER was introduced into the market, which is, let's say, roughly 12 years ago now. A professor from Russia, Professor Entov, that some of you might have heard about from papers in that field, had the first ideas coming to the CaBER and how that looks like. I'm going to show you in a second. And he worked on that with Professor McKinley from MIT in Boston. And the system was then commercialized by a spin-off company from the MIT called CPG, the Cambridge Polymer Group. And that is where we stepped in because they just didn't have the means of really commercialize it correctly. So this is why we found an agreement and we took that over from them. Okay, so the presentation today will be resolving around the CaBER, as I said already, capillary breakup reometry. What is different when we talk about extensional rheology compared to normal steady shear flow experiments? What you see here is the three main deformation flow fields we know in extension, and the one that I'm going to jump in more detail today will be the uniaxial one that you see here. I won't lose any words about the biaxial and planar, more squeeze flow applications. We're just going to focus on the uniaxial extension that is most prominent in most technical applications, and that is the flow field that drives the CaBER experiment. Okay. What is the main difference in terms of kinematics of the two flow fields? When you look at the most well-known flow field in rheology, this steady shear flow experiment, what you see is that you have parallel streamlines in the laminar flow field, and you have a velocity gradient vertical to the flow field. Okay, this velocity gradient we all know we call shear rate. However, when you run into extensional flow fields, especially uniaxial extensional flow fields, like, again, we talk about this in more detail later on, when you want to spray something, when you roll coat something, when you extrude something through a die, in uniaxial flow field will actually evolve, where you have the drawback that you have converging streamlines that then result in a velocity gradient in the direction of the flow. Okay, and this has, of course, a severe impact on your fluids, on the structures in your fluids, and we're going to go over them in more detail on the next slides. Here on this slide, an example of what will happen to your structure in comparison between a shear flow field and a uniaxial extensional flow field. What you see here in the first picture is just a droplet from an emulsion or so in the laminar flow field, but this droplet, this spherical structure, can be also just a model for your polymer coil, of course. What you see in a shear flow field is that this spherical structure is only deformed more or less to some kind of ellipsoidal structure. Depending on the shear rate, okay, on the characteristic speed of your flow field, you will come more or less to an ellipsoidally deformed structure. And we all know that any kind of structure does not want to be deformed. Nothing wants to be deformed. So this is already a fairly harsh deformation. And we know what happens when we deform structures. Entropy will always be in the structure's neck and tell the structure to relax back to its initial state, because it's entropically, of course, the most stable, energetically spoken, the best state. And some of you might know already that those back relaxation processes, okay, that we then can measure as first normal stress difference, or the elastic component in small amplitude oscillatory shear, the G prime, the so-called elasticity, is what causes many problems in applications. And again, we dig into more detail later. But now when you see this, and you know that this is pain already for the structure in your fluids that you work with, imagine how much pain your system feels when you actually extend it. Okay, here you see what's going to happen to your structure in an extensional flow field. Just a flow through a nozzle or a die in whatever kind of machine. What you see is that you don't deform your structure from more spherical to more ellipsoidal. No, you really stretch your structure. You grab it on both sides and really pull it apart. Okay, now you can imagine that the reaction of your structure towards a deformation like that will be very different towards the reaction it shows towards a shear flow field, where you go just from spherical to ellipsoidal. And this response of your structure, of your fluid, towards a very harsh uniaxial deformation is what we need to quantify in order to understand flow anomalies that happen in industrial processes or applications. And this is what we do with the CABER, but more on that later. Here on that slide, just once more, you see the flow fields in steady shear versus extension. And of course, as the mode of deformation is something completely different, one from another, we have to use a different group of material functions to actually quantify the effects of your fluid towards a certain flow field. And this is why we have to introduce new parameters, material functions for extensional rheology. We will talk about the HAAKE deformation, okay, which is nothing else but the natural logarithm of the rate of extension. Okay, and this epsilon that you see here is very much comparable to your strain or deformation that you know from shear flow. Okay, but it's of course an extensional strain and not a shear strain. Then we have the rate of deformation, or HAAKE rate of deformation, okay, which gives you the temporal change of your sample length in regards to the instantaneous value. This parameter epsilon dot is very much comparable to your shear rate, gamma dot. Okay, but again towards an extensional flow field, not a shear flow field. Then, of course, a very important characteristic, and you will see that later on, is the extensional viscosity. Okay, most of you know what the viscosity is, of course, and some of you might be in the situation that engineers ask you for a certain viscosity of a certain batch, and then often you do the shear test to derive a viscosity at a certain characteristic speed. However, when in the processing step that you need to model, or in the application that you need to model, like swallowing or something, extensional flow behavior is prominent, then the viscosity that you need to use actually to model the fluid's behavior towards the flow field is the extensional viscosity. And you will see that the extensional viscosity, eta E with index E, is very different to the shear viscosity eta. Okay, for purely Newtonian fluids, and I'm going to show you plots later on, the extensional viscosity is in comparison to the shear viscosity, just 3 times the value. Okay, this value comes from the so-called Troughton ratio or Troughton number, deriving directly from just the pure stress tensor for a shear flow field and extensional flow field. Okay, I don't want to go into too much detail in terms of math today, but this Troughton ratio is just deriving directly from the 3-dimensional stress tensor. For Newtonian fluid, the extensional viscosity will always show 3 times higher extensional viscosity than shear viscosity. However, for non-Newtonian fluids, this will change dramatically. And again, we talk about this in more detail here in a second. So how can we now test the extensional behavior of fluids? We do that with, as I said already, the CABER capillary breakup extension reometer that you see here, the unit. Again, it was developed by Cambridge Polymer Group with the help of Professor Antov from Russia, from Moscow. And then it was commercialized by us. Here you see how it looks like more open. One of my colleagues is filling in sample there with a syringe. All you do pretty much is you bring in some sample between those two plates, then you let the upper plate move up, and you're going to monitor how the capillary forces, and we talk about the force balance here also in a minute, how the capillary forces will squeeze the filament that builds up together. And then all you need to do is you need to monitor the decrease of the filament with time with just a laser that goes through here, and from there you can then calculate not just the extensional viscosity but also extensional relaxation times. And why that is important, again, I show you practical examples a little bit later on. So here again in a schematic, what you do is you pull the plates apart after some initial rearrangement of your fluid column by gravitational sag. The driving force of the experiment will be the capillary force, okay, the capillary pressure, and this will really squeeze this filament together, and then that force will be carried by, some part will be carried by surface tension, some part will be carried just by the viscous behavior of the sample, and then at one point or another, when you have non-Newtonian fluids, it will be carried by the structure, and this is then when the magic happens, something I'm going to show you here in a second. So what you just monitor is really just the diameter as a function of time. Here shown for 3 different types of samples: blue purely Newtonian, red non-Newtonian shear thinning, and black for an adhesive that dries in. And what you will see, and again I'm going to show you more practical examples here in a minute, is that for the Newtonian case, the viscosity that you read, the extensional viscosity, will be exactly 3 times the shear viscosity. However, for non-Newtonian fluids, here we use the Boga fluid, so very, very low concentrated polymer solution in high viscosity matrix. You will see an increase in the viscosity. That is what we call strain hardening, and I'm going to go over the details here in a second, what that means and how that affects the flow behavior of your samples. So here is just a series of pictures that you see for specific samples. First, a Newtonian case. Fortunately, I could not implement a nice video because something didn't work out with the platform we are using right now. So just a picture series for now. What you see is for the Newtonian case, when you just use a purely Newtonian oil, the breakup is fairly fast. You don't see a real filament build up. It tears apart fairly fast, let's say, okay? You have that pinch off very fast because there is no structure. There is no polymer material, for instance, in there that can actually carry some of the deformation that you bring into the fluid. That changes completely when you have a polystyrene solution here, for instance, where you can see that a real filament builds up, and this filament really necks down very, very slowly as a function of time. And as soon as you measure that, you can then calculate the extensional properties. Okay. A lot of people ask us, well, what kind of instrument is the CABER then? Is it like a controlled stress? Is it a controlled rate reometer? And I think we have some problems here with the font. I apologize for that. Well, all I can say towards that is that, of course, it's not a controlled stress reometer because the capillary pressure varies with time, because it is directly dependent on the diameter itself, as well as the rate of deformation. Okay, also that varies with time because it's also dependent on the diameter. And as the diameter is decreasing with time in the capillary breakup experiment, also the capillary pressure and the rate of deformation will vary with time. So you can say more or less that the sample itself chooses under which conditions it's being measured. Okay. However, those kinds of space time-dependent flow fields driven by capillary forces are very, very prominent in many industrial applications, okay, and in many industrial flow anomalies that you see, like dice well behavior, atomization, misting, roll coating, but more on that a little bit later in the practical application section. I don't want to use too much words here on the force balance we have to consider for the CaBER experiment. For those of you that are interested in that, let us know afterwards. I can distribute some specific literature on that, but I don't want to go too deep into the math here today. So just that you know, as I said, you have the capillary pressure that drives the experiment, and then this capillary pressure is balanced by the viscous stress of the matrix fluid, as well as the elastic non-Newtonian stress. Okay, so when you actually start to unravel your polymeric structures, that then will lead to the strain hardening behavior that I described earlier, that I'm going to show you again in more detail here on one of the next slides. Just one quick slide about the specifications in terms of Haake strains. For those of you who are familiar with different methods, we can go up to roughly 10. Okay, strain rates we can apply in the range from 10 to the -1 to roughly 300 reciprocal seconds. We can cover a wide range of viscosities. Okay, 10 might be a little bit too low. There have been many publications on what are the actual measuring limits for the CaBER, and most of those publications were saying, well, let's say 20 to 30 millipascal seconds should be the viscosity to get a good enough data resolution. On the high-end viscous side, we don't have any limits. You can go up to millions of millipascal seconds. The one really deciding factor for if any CaBER experiment will work or not is the yield stress, but more on that later. We have different plate diameters. Temperature range is 0 to 80. It's liquid temperature controlled. 10 microns is the laser resolution. We can sample with 10,000 hertz, which has a lot of course, advantages when you have fast breakup processes and whatever, like coating applications, but also more on that later. What are the typical areas and applications that we work in with the CaBER? Usually, our customers come from the industrial R&D segment, as well as the academic area. However, we have more and more interest in the QC area when it comes to certain types of coatings. The applications itself that we look into are mainly out of, let's say, 4 main areas. That's the big area of paints and coatings, okay, because all the coating processes, no matter if it's a roll coating, a curtain coating, offset printing, whatsoever, most coating and printing technologies incorporate very, very severe extensional flow fields, okay, and that is why that industry is so keen on understanding the extensional behavior of their systems towards that flow field. Food is a huge area for us, okay, the so-called mouth feeling when you chew something, as well as when you swallow something, is very much dependent on the extensional behavior. The resins, and of course personal care products, so any kind of let's say polymer solutions and emulsions. So what you see in a CaBER experiment, and I explained that already, is that your diameter is decreasing with time. Some of our customers make the mistake that they want to evaluate the data right away as soon as it shows up. However, up to a certain threshold value that can be calculated for a certain material, the flow field, and I was talking about that, is dominated by gravity, okay, and not by the capillary forces and the surface tension. So you have to wait to a certain threshold value that is usually in the range of, let's say, 1 millimeter to 0.5 millimeters. And after surpassing that threshold value, then the flow field will be purely dominated by uniaxial extension. And that is where you can actually apply the analysis that I talk about here in a minute. So why is extensional viscosity so important? I mentioned that already on one of the first slides. When you have a purely purely Newtonian fluid, I said the Troughton ratio tells you that the extensional viscosity will be exactly 3 times the value of your shear viscosity. However, when you have a shear thinning fluid, a polymer containing fluid, polymer solution, polymer melt, whatsoever, at one point or another in shear you will see a decrease in viscosity. Okay, it's a time scale discussion that we lead there. At low shear rates, your system has enough time to relax while you deform it. You have a dynamic equilibrium. At one point or another, at higher shear rates, the time scale you work at gets shorter and shorter and shorter, meaning your system cannot relax anymore. You will have more and more disentanglements, for instance, in your polymer solutions. You go from what we call linear to non-linear behavior. The viscosity is going down. Okay, and what you will see for the exact same polymer solution in extension is the exact opposite. Okay, the viscosity will actually go up with increasing characteristic speed, and that is the result of this what we call strain hardening coil to stretch transition. Remember the slide where I showed you the mode of deformation? You really grab your structure at both ends and pull them apart so that you actually start to unravel polymer coils. Okay, as soon as that happens, your viscosity will increase. Okay, and this factor of increase can be enormous. Okay, you can go from a Troughton ratio of 3 in the Newtonian, in the linear flow regime, to Troughton ratios of tens and hundreds of thousands. Okay, meaning the viscosity that you need to model specific behavior towards a certain application needs to be the extensional viscosity and not the shear viscosity. Okay. Here again, just one more slide. I just skip over that. It just tells the same story that I told you before. Let's look into some applications here. Roller coating application. Okay, you have something that we call misting behavior in that application. You apply your coating via a roll on your whatsoever substrate, and the question now in that industry is, of course, how does my film actually tear apart? Okay, will there be filaments that form, neck, and then break up evenly, or will you have stringiness? Okay, and what you can see for roll coat applications when you do CABER experiments here, a set of data delivered by Professor Willenbacher that worked at BASF back in that time, now is a professor here in Karlsruhe at KIT. He showed a very good correlation between short breakup times and less misting behavior. The shorter the breakup time of a specific sample in that respect, the better it will work in a roller coating application. Okay, same accounts for different paper coatings. Here you just see that in the shear behavior that we looked at for 4 different formulations that worked from very well, here the sample in black, to not so very good, the sample B1 here in blue, you see almost no differences. The shear behavior is almost the same. However, when you do it in the CABER experiment, and I'm going to dive into some more detail why the extensional behavior is more sensitive towards differences in, for instance, molecular weights of polymers or even molecular weight distributions. You see severe differences between the sample that does not work well, here the B1, towards the one that works well, an A1. So a very simple correlation of short breakup time means good formulation for a certain process. In one way or another, some of you might have done it yourself or seen it done by colleagues. The CABER is pretty much nothing else but an absolute approach to the good old 2-finger test. Okay, a lot of people in industry still, when they need to evaluate between or distinguish between good or bad batch for a certain application, they take some sample between their fingers and pull the fingers apart. And just by watching how the filament breaks down, they know if something will work or not, which is fair. However, you need a lot of experience usually to do something like that. And the CABER gives you an absolute approach towards a test like that. Okay, I don't want to spend too much time on every single application. That's a cardboard glue one. We have specific application notes on that we can distribute later on if you're interested. Same thing accounts for wall paints. Okay, will you have squirting behavior or not? Again, we were able to show very quick and reliable that long breakup times show pronounced squirting behavior for wall paint when you apply it to your substrate versus short breakup times that show almost no squirting behavior. Okay. Same when you go from the filament evolution as a function of time, you can directly then via the software calculate the extensional viscosity and the strain hardening behavior that you see here. Okay, for the long breakup times, you have a lot of strain hardening. For the short breakup times, they almost behave Newtonian also towards an extensional flow field, which is important in that respect. One project we did with the CaBER also was in the area of cosmetic products. It was a shampoo, a shower gel that needed to be filled in a standard filling line. Okay, that you see here. So what's going to happen is that the bottles just run through here, and the nozzle opens up and shuts down when depending if there is a bottle or not. However, when your system that you use is too elastic, when you have too high molecular weight component in there, the filament that builds up will not tear apart when you release the pressure. It will stay there, and you will carry this thread from one bottle to another. Okay, for many people that might not look like a huge problem, and that's what we told them. It's like, well, I mean, you have some sample on the bottle, can't be that big of a problem. However, he said the cleaning step would be more expensive than the container and the product together. Okay, so he needed to have formulations that did not show the stringing behavior. And again, this could be correlated directly via the extensional viscosity derived from the breakup times themselves in the CaBER experiment. Okay. Same accounts for the extensional viscosities that you see here for those shampoos. And remember, when you see that data, always think about the shear data that I showed here. They almost look the same. There is not many differences between the different batches that we tested here. The flow curves, the shear viscosity as a function of the shear rate look more or less the same. Again, when you look into the same samples in the CaBER experiment, in extension, you see pronounced differences in the breakup behavior, ranging from 2.5 to almost 8 seconds. Okay, and from that you get, of course, much different extensional viscosities. Okay, they differ by an order of magnitude. Okay. One big application for the CaBER over the last years is the whole area of petroleum industry. So when you use chemical or polymer flooding and enhanced oil recovery, what you do is you drill an additional hole for an injection well, and then you pump, let's call it something now, into the new hole. Can be water for secondary oil recovery, or can be surfactant solutions or polymer solutions for tertiary recovery that you need to press in there to mobilize the oil. You need to lower the viscosity, form emulsions to just get more oil out of the well than you get out by just the hydrostatic pressure that is prominent in the reservoir itself. And what's going to happen to your polymer solution, no matter if it's for enhanced oil recovery, it's a retention fluid that you need to develop, is that it has to pass through the pores in the porous media where the oil is trapped in. Okay, and what's going to happen is the same thing as when you squeeze something through a nozzle, like I showed you on the one of the first slides, is that the polymer coil here is actually extended. Okay, it's extended when it goes through the pore. You go from a large diameter laminar flow field to a small diameter laminar flow field, and during this transition between the laminar flow fields, you have flow instabilities, Taylor vortices that will then actually tear the polymer coil apart. And now when the polymer has not enough time between two pause, to relax, it will eventually break. And when that happens, the material's behavior is not what you expect, is not what you need anymore. Okay, and that is why you need to look into the extensional properties. And the flow field that is prominent there is the exact same thing that you do with a CABER. And what you see here, we tested a specific polymer in 5,000 ppm concentration in saltwater brines. And what you see here is that depending on the temperature, the flexible coils show, of course, much shorter relaxation times. Okay, so you can actually model the behavior of your systems in the reservoir on the CABER. One case study I want to present you that is supposed to show you how sensitive the method itself is towards differences in molecular weight and molecular weight distributions, is a story of a project that we did for a certain customer that had the problem that he got a specific polymer delivered from his supplier, and as always the supplier says, well, the polymer is the exact same. The same means the molecular weight is the same. Okay, and when we talk about the molecular weight, or when you talk about the molecular weight, most people talk about, let's say, one mode of the molecular weight distribution. So let's say the weight average. Okay, the weight average molecular weight might be the same. However, the actual application behavior of a certain formulation is very different to another. And our customer had no means of explaining that, because the shear rheology always looked the same. However, the systems behaved completely different in the real-life application, and they approached us asking us if we can find the answer for that. So what we did is to show the feasibility of that. What we did is we designed some very specific polymer blends first to see how sensitive the CABER actually is. Meaning we had 6 different polystyrene blends that we designed in a way, or that we have here the 6 different polymer blends that we blended from 6 different polystyrene standards in a way that the weight average molecular weight was supposed to be always the same. However, the molecular the polydispersity, meaning the width of the polymer weight distribution, or the molecular weight distribution, differed. Okay, and then we tested those differently distributed polymer blends in solution in shear, for instance, and you see that the shear curves are always the exact same, because the shear viscosity is a function that actually is looking only at the weight average molecular weight. Okay, so not just the zero shear viscosity, but also the transition from linear to nonlinear behavior, Newtonian to nonlinear to non-Newtonian behavior, is given just by the weight average molecular weight. Okay, the width of this transition. Okay, how sharp is this transition might tell you something about the width of the distribution via the Carreau model, the B parameter in the Carreau model. However, it is not very sensitive to small differences. When you look at this at the same polystyrene blends now in a capillary breakup experiment on the CABER, is that you see huge differences in the breakup behavior. Okay, huge differences in the breakup behavior, and not just in the breakup behavior, but then of course resulting in the viscosity and also the relaxation time. And what we found out is that the best mode actually of the molecular weight distribution that correlates with the extensional behavior is not the weight average molecular weight, but it's one of the higher modes, the Z average, the centrifuge average of the molecular weight distribution. So you see already that you see huge differences here, just depending on the molecular weight distribution. All those 6 samples have the exact same weight average molecular weight. Keep that in mind. However, we needed to transfer all that we did theoretically on something easily described like polystyrene in DEP on the actual sample that showed problems, namely a cellulosic derivative, okay, where our customer got delivered always the same quality as the supplier said. However, what we found out when we looked into the molecular weight distributions for those samples is that they have roughly the same molecular weight, average molecular weight. However, the higher modes were way different, so that the polydispersity of those samples was, of course, also different. And what you see is when you look also in a more complex polymeric system, like a cellulosic derivative in water, is that in shear and oscillation, there was almost no difference that could be made. However, our customer was very specific in saying, well, one of those samples will show a very good behavior. Those samples were used as thickener agents in building materials, okay? So plasters that were sprayed to the substrate. Some of them showed very good behavior. The other ones did not. And again, rheologically, he needed an answer why that is so. And in shear and then oscillation, we see absolutely no difference. Whereas when we look into the CaBER experiment, we see huge differences. Okay, we see very distinct differences in the breakup behavior here, and those will then again translate into very much more pronounced differences in the extensional viscosity and also the extensional relaxation times that then can be used to actually mimic that process. Okay, so with that, I want to go into this summary already. I was able to explain you that extensional flow fields are, of course, prominent in many different technically relevant flow fields, and that rotational reometers cannot predict how those fluids will behave towards those extensional flow fields. Okay, with the extensional viscosity and the extensional relaxation time, you have much better tools of correlating a certain formulations or products behavior towards a certain processing or application step, and that extensional viscosity is even much more sensitive towards the high molecular weight content and its influence on the flow behavior itself. So even samples with the exact same weight average molecular weight that might behave differently in certain processing and application step can be probed for with a CaBER experiment. All right, with that I want to close and thank you very much for your attention.